Okay, so this morning I'm going to record a short lecture on a review of fluid balance. These are concepts that you should have learned starting with basic science classes back in high school and through your anatomy and physiology, chemistry classes in college. Okay, it's just going to be a short review of concepts that are important for you to know throughout your nursing career. Alright, so first, let's talk about the essential concepts of fluid balance. You need to understand what the functions are of fluids. This is something that you'll hear me say throughout pathophysiology, is if you don't understand the normal function of whatever system or chemical or enzyme or hormone that we're talking about, then you're not going to understand this function of it. So, remembering and learning and understanding the functions of fluids in the body is essential. That's like the foundation of understanding fluid imbalances. And if you don't have that foundation, then your understanding of fluid imbalances will collapse like a building that doesn't have a good foundation. All right. So then you also need to remember, where is the fluid located? How does fluid move in the body? Because that's very important for maintaining balance. And also how fluid balance is maintained through homeostatic mechanisms. And you learned a little bit about homeostatic mechanisms in the first part of Introduction to Pathophysiology. You should have learned about that before too, but you know. All right, so first let's consider what are the functions of fluid. Now I want you guys to think about this, so pause the video and think about what are the functions and come up with at least 4 functions. And then I'm going to write some in. Okay, so what are 4 of the functions? Because I'm sure there's many more functions that we don't even think about. One of the things I was thinking about today is that I was reading, again, a review every time before I do a lecture, and I look at different sources. And one of the sources I saw today is humidifying air going into the lungs. I had never thought about that, but it's true. Think about if your mouth and your throat, your nasal passages are all dry, then the air that gets into your lungs is dry and it's irritating and it'll dry out your lungs. It's not a good thing. So that's one of the functions of fluid in the body. One of the more common functions include, well, that's not a very good color there, is it? Transport of what? Nutrients and wastes, right? Transport of nutrients and wastes. So we transport nutrients to the cells and wastes away from the cells. We transport blood around the body. Ooh, that's another one. Transport blood around the body. Blood cells, because those do different things. Remember, we're not just talking about red blood cells, we're talking about white blood cells. We're talking about fractions of cells, which are platelets. So the transport of different types of blood cells around the body. What else do they do? Metabolic reactions and processes. You have to have fluid for metabolic reactions and processes. So metabolism, metabolic reactions and processes. What else? What else do we need it for? Let's see. Do you sweat when you get hot? Yes, you do. Fluid that moves around the body in blood from the core of your body to the outside helps keep you warm and keeps you cool. So temperature regulation is also a very important function of fluid. So those are four functions of fluid. There's other functions. It protects your organs. It helps keep your skin moist and as a good barrier. There's lots and lots of different kinds of functions of fluid in the body. Okay, so now let's look at where the fluid is located, because that's another really important concept, is remembering where is the fluid located. And here's a little graphic. I'm big on graphics. I like graphics because I know people like to learn sometimes by visualizing. I'm also big on repetition. I know the video that I signed, the fluid and electrolytes made incredibly easy. Some of this may be repetitive, but repetition, hearing, writing, reading is sometimes a very important practice in learning new concepts and reviewing old concepts. Okay, so there's two main compartments of where the fluid is located. Okay, there's the intracellular and the extracellular. Now, shockingly, the intracellular fluid is actually more. Now, I want you to look at this because this can be a little confusing, because this person here, when we're looking at it, this is where the fluid is. This is other stuff, salts and cell, you know, the dry stuff. That if you ever used to watch Star Trek, the old Star Trek back in the day, there was an alien life form that would like suck all the fluid out of body, and it would turn them to dust. It would just turn them to powder. And so this stuff up here would be the powder left over if you took all the fluid out of your body. So this is the amount of fluid that's in your body, okay? And we'll talk more about what total body water percentage is in a minute, but right now we're looking at the compartments, okay? So this is the intracellular compartment. That means all the fluid that's actually within the cells. That's this compartment. And it is approximately, in a normal male that's not obese, an average size male who's not obese, is about 25 liters, okay? That is intracellular. If you add together the extracellular fluid that we have here, you would have 3 liters, which is the plasma, the fluid that's in the bloodstream, and this is the fluid that's outside the bloodstream but not in the cells, interstitial. There's also transcellular fluid, which is a very, very small amount of fluid, and that's fluid that's in your cerebrospinal fluid and in your joints and in your eyeballs, stuff like that. Fluid that might be surrounding your organs. It's a very small fluid that might be between the pleural membranes, or in the between the peritoneal membranes. Very, very, very small amount of fluid. So most of the fluid is in the intracellular compartment. That's in the cells. And then you have a little bit of about 15 liters outside the cells, and then a very small amount in the transcellular fluid. And those are the fluid compartments. Okay, now this is distribution of fluid, and it's actually very interesting because people don't understand that the total percent of body water in a person is dependent upon several things. Gender. So gender is a factor that helps determine body, the percentage of water in the body. And I'm gonna write these up here because we're going to talk about them a little bit. Gender. Okay. Age, and body habitus. When I say body habitus, I'm talking about very thin people, or you have a normal body habitus, which is considered a normal body weight, or somebody who's obese. That's their body habitus. Okay, so gender, age, and body habitus determine the percent of body water. Okay, so if you look down here at the bottom, you can see that children have a high percent of body water, and then this is based on an average adult, not fat, not thin, is about 60 to 65% body water, and then an elderly person is 55%. Now, this is one of the things I want you to think about, is that adipose tissue has less water than muscles. So any kind of fatty tissue has less water than muscles. So people with an increased percent of fat tissue, adipose tissue, have less water. So let's think about that. Women, because of breasts and hips and the fact that we are made the way we are made, have a higher, in general, have a higher percent body fat than do men. Men tend to have more muscle mass than women do, percent-wise. And again, that's breasts and hips and this adipose tissue that God put on us because we're women. Okay, so women tend to have less total body percent than men do because of our fat content, fat percentage. Okay, so that's one way that explains the differences in total body percent water. As we age, we lose muscle and we increase because we lose a percent of muscle. That causes an increase, a reciprocal increase in the total body fat. So as we age, we're going to lose some of our muscle and we're going to gain body fat. That's why the elderly have less water than adults. Okay? So then if you think about that, and we've talked about why women have less water and why the elderly have less water, then people who are obese that have a higher percentage of body fat than normal body weight people, they're going to have less water percent or less total body water than people who have a normal weight. So those are the ways that you look at it, and what it all boils down to when you look at this truly is the percent of body fat or adipose tissue. That's what does it, right? So you need to think about that, and this is something that you should consider because somebody who has less body water is more likely to have problems with overhydration or dehydration. That's just the way it is. So you need to think about that when you're looking at your patients. So women who are overweight and elderly have the least amount of water than anybody except for newborns, just about. Okay? I'm sorry. Yes, they definitely, because children are mostly water, while elderly adults are less water. They have the least amount of water. All right. So now we have to look at how fluid moves, because this is another important issue. Because a lot of times we maintain a normal amount of fluid, okay, but fluid is constantly moving around in our body between cells, into cells, out of cells. Sometimes we excrete it, but we're always taking in. So we tend to maintain a certain amount of fluid, and that's due to homeostatic mechanisms, but our body functions because fluid and electrolytes move by these three, well, there's actually probably more ways that fluid can move, but these are the three most important ones that we talk about. I mean, there's active transport and there's facilitated transport and stuff like that, but we are going to talk about diffusion, osmosis, and filtration. One of the things you have to keep in mind here is that fluid compartments in the body have membranes that are semi-permeable. That means that some things will move through and some things won't. So sometimes water will move through and solutes won't. Sometimes solutes will move through, and sometimes, fat can. It just depends on what kind of membrane it is and what actual movement process is occurring. Okay, so diffusion is when solutes move from an area of high concentration to an area of low concentration in a process of trying to equilibrate concentration. Okay, so you have a semi-permeable membrane, and you have different concentrations of solutes on one side and the other. So you might have a high concentration of solutes. Now remember, concentration is based on the same amount of fluid on both sides of the membrane. Okay, so when we're talking about diffusion, you have the same amount of solvent on both sides, but you have a different concentration of solutes. So what happens is the solutes move across the semi-permeable membrane and the function is to equilibrate the concentration of solutes. Okay? So, but not all solutes can move across the semi-permeable membrane. You could have solutes of sodium here, and then you could have also solutes of calcium. Well, the calcium can't move because this membrane is not permeable to calcium. That's just an example of what a semi-permeable membrane means. Now, why is this important related to fluid balance? Well, one of the reasons it's very important to fluid balance is because water follows sodium. So if a membrane is permeable to sodium, then water is going to follow it. This is really important when we start talking about aldosterone and fluid balance in a few minutes. Okay, so remember that. Water follows sodium. They're like best friends. They freaking hold hands everywhere they go. Okay, so give me an example of where diffusion happens in the body, and it doesn't even really have to be related to fluid. If you think about it, you have to start with the concept that blood returning to your lungs is lower in oxygen than the air that you breathe into your lungs. So you breathe air into your lungs that is higher in concentration in oxygen than is the blood. So the oxygen moves across the semi-permeable membranes in the alveolar capillary junction. There's a alveolar capillary membrane there. Okay, let me draw an alveoli. I'll draw an alveoli. This is an alveoli. And then it is surrounded by, oops, let me draw that back again. Sorry about that. All right, that's the alveoli. And now I'm going to draw the blood that's going to surround it. This is a capillary surrounding it. So what happens is when you breathe in air, when somebody breathes in air, okay, and I'm going to make the air pink because it has oxygen in it, the air comes in, and because there is less oxygen in the blood here than there is in the alveoli, that oxygen starts to move across into, it moves across that membrane, moves across that membrane into the bloodstream. That's diffusion. So one of the things I want you to think about now is, well, what happens to carbon dioxide? You know, in your blood right here, you have a higher level of carbon dioxide than here in the air that's coming in, so the carbon dioxide is going to move out of the blood and into the alveoli, so then you can get rid of it. That's one place where diffusion happens in the body. I'm sure you can think of lots of other places because it happens in many, many, many places. Okay? All right, so in osmosis, a key concept related to osmosis is only fluid moves. Okay? So you have two compartments, or two compartments, and you might have one that is very concentrated, but they don't have, and they're not in there, and it doesn't necessarily have to be. Remember, when we talk about concentration, concentration is determined by the amount of solute and the amount of solvent. And I like to think about that as, well, when I make lemonade. If I put a lot of lemonade powder in the water, it's going to be very lemony. It's going to be too lemony, it might be too tart, right? Well, the same thing can happen as if I put the correct amount of lemonade powder in too little water. It could have the same concentration of me putting too much powder in water as if I put the right amount of water and right amount of powder in too little water. I want you to think about that for a minute. Okay, I'm going to make lemonade, and I think the directions say I'm going to use 1 cup of lemonade powder to 1 quart of water. Well, that's very lemony. That's too lemony. So I go back and look at the directions, and what the directions actually say is I'm supposed to use 1/2 cup of lemonade powder, to 1 quart of water for it to be the right concentration. So there, in the way I made it with 1 cup to 1 quart of water, I have way too much solute. Too much solute, okay? So what would happen though if I read the directions and I thought it said 1/2 cup of lemonade powder to 1 pint of water? Well, the same thing happens. I still have too much solute, but that's because I don't have enough solvent. Okay, I have the same amount of solute but it's still too concentrated because I don't have enough fluid. So when you're thinking about fluid compartments and concentration, you have to keep in mind, is it because there's a higher amount of solute? What's the total amount of solute versus what's the total amount of fluid? Okay, so when in osmosis you pull fluid from an area of low osmolarity, and all osmolarity means is concentration. That is a fancy way of saying concentration. That is how much solute is in solvent based on osmoles, which is a thing in chemistry. It's a way that they measure concentration in chemistry. Okay, so you're going to move fluid from an area where there is low osmolarity, which means that it's low concentration. There's a lot of water, low solutes, that's low concentration, to an area of high osmolarity to try to make it the same concentration, because we're moving fluid. We're not moving solutes, we're moving fluid. And that has to happen through a semi-permeable membrane. Okay? Alright, so moving on, I want you to tell me, where does osmosis occur in the body? Well, the most frequent place that we think about it occurring in the body is in the kidneys, because or in the bloodstream. Alright, so let's look at it in the bloodstream. If this right here is my blood vessel, okay, and my blood vessel, my blood is supposed to be around 240 is the concentration. That's just a unit, 240 units per mil. I'm not worried about what the units are or anything like that, but within the blood vessel, the concentration is supposed to be 240 units per mil. Okay. Well, outside here, this is supposed to be 240 units per mil too. That's homeostasis. Fluid moves in and out of this. Fluid moves in and out of the cells in the interstitial area. It moves in an effort to maintain homeostasis. All right. So out here, we have 240 units per mil too. What happens if you don't drink anything for a while and the concentration in your bloodstream goes up? It gets more concentrated to where it's 400 units per milliliter, and you're not drinking any water or anything. What is going to happen here? You're going to move fluid from an area of low concentration, low osmolarity, because this is lower than this, into the bloodstream in order to make this similar concentrations. They want this to be equal to this. Okay? That's one place where osmolarity occurs. Okay, we'll talk about other places when we start talking about fluid imbalances, and further on when we start talking about pathophysiological processes. Now, filtration is, I want you to think about this. If you're filtering something under pressure, you have a hose, okay, and a pump is putting pressure on the fluid in that hose. Let's make it a little bit more interesting. Here's your hose, and it's a blood vessel. Your pump is your heart. One of the cool things that your body can do is either increase or decrease the size of your hose, and that would also increase pressure. Okay? The volume is also a factor related to pressure. The more fluid you have in your blood vessels, the higher pressure it's going to be in there. Now, this is vascular resistance, is being able to make these bigger or smaller. Your vascular resistance goes up as you make your vessels smaller or vasoconstrict. It goes down as you vasodilate. Contractility of the heart is how hard and how fast it's pumping. Okay, so all that causes increased pressure within your blood vessels. Now, when you get to your capillaries, your capillaries have these pores. Okay? And these pores allow stuff, different things. It can be fluid, it can be solutes, it can be electrolytes, it can be nutrients, it can be all kinds of stuff to be filtered out of the blood vessels into the surrounding area. That is filtration. And it is related to a porous membrane, which right here we're talking about capillaries, and hydrostatic pressure. Okay? And the hydrostatic pressure I just talked about. If you need to review that, back it up and review it. Okay, so where does filtration occur in the body? It occurs in the kidneys. Because what happens in the kidneys is blood comes in. I'm going to do this in pink so you can see it here because there's nothing pink on this one. You have blood that comes in here under high pressure, and fluid comes out, sugar comes out, sodium comes out, all kinds of stuff comes out into the glomerulus, and it becomes part of the filtrate, which is eventually concentrated into urine. Okay, so this is a nephron. This is a functional unit of the kidneys. High pressure here. Okay, all the stuff that needs to and probably more comes out here and becomes part of the filtrate, which is eventually concentrated down into urine. And here's one of the things I want you to think about. Urine is concentrated through the processes of osmosis and diffusion in the tubules in the kidney. Stuff you should have learned back in A&P. All right, so now we're going to put it all together, and this is a very confusing kind of slide, but let's look at it one thing at a time. Now remember, the first thing I'm going to talk about is I'm going to talk about hydrostatic pressure. That's the last thing that we just talked about on the last slide. Okay, is hydrostatic pressure. So here is hydrostatic pressure right here. It is orange. See here? Hydrostatic pressure orange. This is the beginning of the capillary. Okay? This is at the arterial end. The arterial end of the capillary. Important concept, arterial end, because it has higher pressure at the arterial end of the capillary. Okay? Higher pressure at the arterial end, lower pressure at the venual end. Okay? So the other thing I want you to look at, which is really important, and this has to do with osmotic pressure, is these little green things. These are proteins. Proteins act like sponges, and that they increase the colloid or oncotic pressure and pull fluid in. There is a higher concentration, a higher pull volume, which is this green stuff, because of the amount of protein in the blood. And you'll see that here, colloid osmotic pressure. That will pull fluid into the capillaries. Okay? So, at the arterial end, though, there is hardly any colloid osmotic pressure, meaning there's hardly any pulling pressure at the arterial end of a vessel. At the arterial end of a capillary, there's hardly any pulling pressure. Okay? So the total pressure here is 9 milligrams per milliliter of mercury, meaning you're going to have fluid moving out here. You will have fluid moving out of the blood vessel here, carrying nutrients and stuff like that. Then here is where you have the change from the arterial end to the venular end. Well, here, remember what's different about veins and arteries. Arteries are very stiff-walled and not very flexible, where veins are. So you have a sudden decrease in the blood pressure here, in the hydrostatic pressure. Okay, so you quit losing as much fluid, and you see that with the little orange arrows, right? But what you do see is you see these bigger green because you've had a decrease in the total amount of fluid here, the total amount of water, so you have an increase in concentration here, and that's a colloidal or osmotic pressure, so it starts bringing fluid in from the interstitium in the cells, which is carrying the waste products back into the blood. And so this is how you look at the total fluid altogether, the total different kinds of pressures here. Okay, this is a really important concept when we start talking about edema and filtration and what happens when you don't have a good blood pressure or cardiac output. That's really important to get this kind of what's happening in the capillaries with different kinds of pressures. All right, so how do we maintain our fluid balance? Well, one of the ways we maintain our fluid balance is by our intake equaling our output. Well, how does that happen? Well, our intake, if you remember watching that incredibly easy video, we take stuff in, we take fluid in through solid food and fluids. Most of us through fluids, but we do get a small percent through solid foods, and also we produce some fluid with cellular metabolism. Okay? The fluid that we put out is through urine and feces. Those are the two measurable. Now this is key. People miss this key concept all the time. We can measure the amount of fluid in urine and feces. Urine very easily, especially if we put a catheter in them. Feces, if we dry it out, if we weigh it, let it dry out, and then measure it again, we can tell you how much fluid was in it. That means they're measurable. But there's insensible loss that we can't measure. And insensible loss includes respirations, sweating, and through our skin, basically, okay? So sweating, and then sometimes we just evaporate too. We just have fluid constantly evaporating. So we actually lose quite a bit of fluid through respirations just from breathing in and out, because when we breathe out, think about if you breathe out on a cold window, it fogs it up, right? You have fluid in it. Okay, so this is just a graphic of how we take fluid in and out. Over here is in, over here is out. Okay, that's how we do it. All right, so there's 4 ways that we maintain fluid balance. The first way is really easy, it's thirst. And then we talk about the RAS system, which is renin-angiotensin-aldosterone system, antidiuretic hormones, and then natriuretic peptides, okay, which are also hormones. Now, thirst is a fluid balance regulator, very easy, although, you know what, by the time we get thirsty, we're actually a little dehydrated. Okay, so that's something that especially in older people. So that's another reason why elderly people tend to get dehydrated more easily. So if we get a little dry, meaning we have our blood is a little concentrated, it becomes higher osmolarity, and that stimulates the thirst center in the hypothalamus. That leads to drying of the mucous membranes, which stimulates the thirst center in the hypothalamus, which makes us want to drink. Okay, so here's a little graphic of that, of how it works. Okay, and here's what happens: is you decrease the total body water, decrease the secretion of saliva, you get a dry nurse, it increases your fluid intake. And then in here, you know, your hypothalamus gets stimulated right here. Okay, so that's how you get thirsty and then you drink. That's one way we maintain fluid. Now, the RAS system is a little bit more complicated because it has many steps. But what you need two main concepts, two very important concepts about the RAS system. When you have decreased blood flow to the kidneys, I didn't say there's a decreased blood volume. I said when there's a decreased blood flow to the kidneys, the JG cells, because I can't say that word, that's juxtaglomerular cells, the JG cells are in the kidneys. Okay? And when the kidneys sense that there's a decreased blood flow, the JG cells will produce renin. Now, sometimes the cause of the decreased blood flow to the kidneys is a decreased blood pressure. Sometimes that could be related to decreased blood volume. Sometimes it could be related to decreased heart contraction in people who have heart failure. Sometimes it could be related to renal hypertension, where the renal arteries are constricted for whatever reason, okay? But whatever it is, there's a decreased blood flow. The kidneys sense a decreased blood flow. They release renin. Then angiotensin 1 and angiotensin 2 are released, and that results in the release of aldosterone. Aldosterone makes a part of the renal tubules permeable to sodium, so that the sodium is pulled back into the capillaries. And when sodium, remember, sodium and water go together. So when the body pulls sodium back into the capillaries, fluid follows. So this is one way that the body compensates for decreased volume. Okay? Now, the opposite occurs too. If you have too much fluid, the body will decrease the amount of sodium that is reabsorbed by decreasing aldosterone production. It's a negative feedback. Remember, it's a negative feedback loop. You have to understand negative feedback loop. All right, so let's move. Here it is right here. Okay, so study this here. This is a feedback loop. This is going to tell you what happens. Okay, and here is where it says it decreases arterial blood pressure, so it triggers RAS. Okay, that's how it happens. And here it'll tell you if you increase, it also decreases urine volume. That's one of the things that it does, is it pulls fluid into the tubule, so you're also going to have a decreased urine output. That's how it tries to compensate for it. It doesn't replace the fluid, but it prevents you from peeing it out. Okay. So water follows sodium, that's how you replace it. Now, antidiuretic hormone is another hormone that helps maintain fluid. But one of the things about antidiuretic hormone is it only works to retain water. It doesn't have anything to do with retaining sodium or messing with sodium absorption or reabsorption. It only works on water. Okay? And the way it works is, well, first off, let's look. It's produced by the hypothalamus, but stored and released by the pituitary, posterior pituitary. That's the storage box for the hormones that the hypothalamus produces, and then they're released from the posterior pituitary. All right. Now, it is triggered by an increase in blood osmolarity. Well, if blood osmolarity is actually the concentration of the blood, how thick the blood is, how many solutes per mil there are, that's an increase in the concentration. That's what that means, remember? So that means your blood's thick. Somebody's blood is thick. And the osmolarity goes up because there's a decrease. The body perceives it as a decrease in fluid. There's a fluid deficit, and the body needs to hold on to deficit to decrease the osmolarity. The body needs to hold on to fluid to decrease osmolarity. So the osmolarity goes up because the blood's more concentrated for whatever reason. There's less fluid. Okay? That's why the osmolarity goes up. So what antidiuretic hormone does is it increases fluid reabsorption, not salt, just water, in the distal tubules. So it makes it selectively permeable to water, so sodium is not reabsorbed. So I want you to think about this. If antidiuretic hormone is being released and is increasing fluid, what happens to the concentration of sodium in the blood? If you think about it, if you're increasing fluid only, that is decreasing the percent of sodium because you're adding more water. That's like if you have 2 quarts of water and a half a cup of lemonade powder, going back to the lemonade where it's supposed to be a half a cup to 1 quart, it makes it like you have a half a cup of lemonade powder to 2 quarts of water. It's less concentrated. Okay? That's what can happen with too much antidiuretic hormone. And here's a little cute thing to think about. If you're old enough to drink, or if you drink, don't you have to pee a lot? A lot of people say, oh, I pee a lot because I'm drinking a lot. No, you're peeing a lot because alcohol actually inhibits the production of antidiuretic hormone. Antidiuretic means no pee. You're not going to make urine, no urine hormone. So if you're inhibiting that, then you're not making it. So basically, you're peeing a lot. Alcohol, oh my God, is a diuretic. It makes you pee a lot. Okay. So here's the antidiuretic hormone feedback system. Okay. And I just want you to see this because it's another way to visualize it. Okay. And the antidiuretic hormone looks at mostly concentration and volume. So you have these volume receptors and osmoreceptors, okay? But it does result in you retaining fluid, okay? That is to restore fluid volume. So this is what I want you to think about because these are key concepts. What happens to the production of aldosterone if blood pressure increases? Because remember, aldosterone is released in response to a decrease in blood pressure. And what happens to the release of antidiuretic hormones if osmolarity decreases? And you're going to answer that in the top hat that I'm going to post. All right. Now, natriuretic hormones. I want you to look at this word. This is one of those really important times where you understand what your prefixes and stuff like that look like. Okay, so sodium, Na is sodium, and atria has to do with your atria. The first one they discovered was in your atrium, so now they just say atria. And then it's uretic, so it has effect on the urine production. Okay, now this works opposite of aldosterone. Natriuretic peptides work opposite of aldosterone and antidiuretic hormone. They are counter-regulatory hormones, meaning that they are stimulated by high blood pressure and high blood volume that stretch the heart tissue or stimulate this osmoreceptor in the brain. Okay, a pressure receptor in the brain. So they act the opposite of aldosterone and antidiuretic hormone. Aldosterone and antidiuretic hormone make you hold on to fluid. Natriuretic peptides make you pee out fluid. That's what they do. They do the opposite. So here it is, sodium and uretic having to do with urine. So the way that these work is they inhibit sodium reabsorption. If you're not reabsorbing sodium, you're not reabsorbing water, so you're peeing more out. Okay, so this decreases blood volume and also decreases osmolarity because you're peeing out large amounts of sodium. All right, now that is the end of fluid volume review. I'm also going to do a short video on fluid imbalances.